Hello, everyone, and welcome to Coffee with Caleffi. Today, we've got a special edition. We've got kind of a panel discussion on balancing. So this is an Ask Caleffi version of Coffee with Caleffi, and we've got a bigger team today, and I'll introduce them in a second. So to get started here, I wanted to talk about a couple of background things. We are still very excited about our win for AHR's Innovation Award for the angle mix. So this mixing valve is something that we're really proud of, and it took home the blue ribbon at AHR this year. So even though we weren't there in person, we'd like to spread the word a little bit more about that. Very cool product. And then Hydronic's 28 is out. That is shipping and it's available online. Something interesting about Hydronics, the new versions are in this cool digital format as well. So you can download the PDF, or you can go to the website and have kind of a smart digital version of Hydronics, or if you've signed up to receive them in the mail, they should be on their way already. Okay, next month, the Coffee with Caleffi is going to be kind of a cool different version as well, where we're going to be talking about a specific job site. So we've got Pete and Gary to walk us through some of the challenges they've had with an existing building and how they've installed some of our plumbing products there and have worked through the kinks of some difficult situations, which I think will be helpful for other engineers in the crowd. And then today, I'll bring the rest of the team on now to introduce everybody. So Cody Mack is one of our education and training managers. Kevin Freidt is our director of engineering. And Dan Firkus is one of our tech support engineers, and he is going to be going over some of the details from calls from the field, which is really helpful. So welcome, team, and I think that I'll show the agenda here, and then we'll start off with Kevin. So today we're talking about the pros and cons of different types of balancing valves. How do we size them? Do you always need special equipment? And what happens if you add something? So to get started, Kevin, do you want to tell us about the different types of balancing valves?
Sure. Hi, Max. How you doing?
Good.
We have basically three categories of balancing valves, and what we'll do is start off talking about the manual type. Here are some sample products in the market, some of Caleffi products and other brands as well. Manual balancing valves, you can think of these as an adjustable restriction in the pipe. That's a really easy way to think of them. They're called static, sometimes referred to as static because once you set them, there's really no moving parts. They are just a restriction in the line. So also called pressure dependent because as the pressure in the system changes, so does the flow. So that's what pressure dependent means. They depend on pressure to be accurate at the settings that they are set to. Okay. Now that setting, once you get this type of valve set, it's only accurate at that given differential pressure. Okay, again, back to pressure dependent. The recirc systems and hydronic systems are not static. So as pressure changes, so does the flow when you use these kinds of valves. Most people think of them as the most basic type. They've been around kind of the original, and typically they're the lowest cost. Not always, but you can think of them as a lower cost type of balancing valve. Most of these, if you look carefully, you'll see that they have two what are called PT ports, and you need a differential pressure tool, also referred to as a manometer, to hook up to these two PT ports to measure the pressure drop across the restriction, and then you correlate that to a certain GPM. And Dan is going to get into that a little bit more too, but the most of these you can see the PT ports. That one on the right with the built-in flow meter is a little different, and we'll talk about that one as well. There are two types of manual valves. We won't go too deep here, but if you hear the term variable orifice, what that refers to is, if you look at this sectional view of the Caleffi 142, as the valve is adjusted, the CV of the valve changes. In other words, that mechanism, the plug and seat here, as you open and close this valve, you're changing the CV or the flow capacity in between the two PT ports. Okay, so that means as you make the changes, you will be changing the flow capacity of that valve. So that's a variable orifice. The fixed orifice type is the two pressure pickups, the PT ports, are located across a venturi, a reduction in the cross-sectional flow area of the valve, also sometimes called a vena contracta if you're a fluid mechanics type of guy. But that never changes, okay? So those PT ports pick up the pressure drop across that restricted area, and the valve adjustment is actually after. It's outside of where the PT ports connect to the valve. So a couple of advantages or disadvantages. The valve on the left, the variable orifice type, is really good if you have super low flows, okay? Because you can crank that plug down to where it's almost closed and still measure the differential pressure. So that's one advantage of the one on the left. On the right, that one will have real difficulty at a very, very small flow, but it has really good accurate adjustment on the higher end. So you typically get more flow range because of the fine adjustment that you can do with the fixed orifice type.
And part of that is based on this shape as well. You know, whatever is closing on the seat there, that's part of it, correct?
Right, exactly. The design of the valve has a lot to do with that. And then Dan will get into the sizing and how you use those charts later on.
All right, we've got one more here.
Yeah, so the 132 series quick setter is different. It is a manual valve, okay? In that circle there, that red circle, you can see where the fixed orifice is located. So it's a fixed orifice type valve. And this one is different though. Instead of having PT ports, we actually install a flow meter between those ports. And that flow meter, when you pull the pin, it will allow a certain amount of flow, a calibrated amount of flow, to go through that flow chamber and activate the flow meter, which then gives you a direct GPM readout. So that's a different type of valve, super popular. This has been a huge seller for Caleffi. And again, Dan is going to get into that a little bit more in a few slides down the road here. The second type of balancing valve is an automatic or dynamic, also called pressure independent. So as you can guess, this one controls a fixed GPM independent of pressure fluctuations. So it's a dynamic valve because it has moving parts inside. As the fluid thrust changes, as the system changes pressures and changes flows, that cartridge that you see down below will open and close a characterized port based on the fluid thrust and maintain a constant GPM. Okay, that's the thing about these. If you want to put in a balancing valve and you want to always know that it's at 0.5 GPM or 1.5 GPM, you can put one of these in. They're very compact, very affordable, and they work great in hydronics and plumbing applications.
And one of the major things that changes here, if you lined up all the different GPM sizes, you would see this characterized opening change very slightly. So it's
Right.
something that's not, you know, a number of centimeters different. It's a very small change. So,
Right.
and
And I
we'll
like,
talk about a little bit later if you're changing things in the system, what to pay attention to there.
exactly. And we have a couple of graphs here that show how that pressure differential and flow are related. So as you come up, say from 0 PSI to 2 PSI with this particular model, you will increase obviously from no flow up to this certain control range flow. And then that middle one where the line is flat, the control range, that's a constant GPM between 2 PSI and 32 PSI drop, okay, DP. And that is really essentially the compression range of that spring. So the opening that Max pointed to will modulate open and closed as we compress that spring to control that constant GPM. And then of course, if you get above the maximum DP, you will increase flow because that spring is completely compressed. So after that, you're just forcing more flow through the valve. So these
And
are
at that
great,
point,
I think.
you're just pushing flow through this little circle if it's completely compressed, right? You've kind of gone
Yeah,
all the way past
right,
the bottom. So there's no control, there's no adjustability there. It's just a single orifice.
exactly. Yeah, and these are good for HVAC coils. For example, most coils are designed for a certain GPM. And so these are perfect for that. You just put it in and forget it, and then they work really well for that application.
Okay, and then
The,
here's the third.
the third type of balancing valve is a thermostatic balancing valve. These are completely different. They actually modulate the flow. None of the other valves we talked about actually modulate the flow. This one changes the GPM based on temperature. Now, these are not used in HVAC or hydronic applications. This is strictly a domestic hot water recirc balancing valve. And we say it's a temperature solution for a temperature problem. It has an element inside that's a lot like a mixing valve. It's a sealed device that expands and contracts to open and close a valve plug. And it responds to temperature. Cool temperatures will make it contract, and higher temperatures will make it expand to close that seat down to minimum. And these, we're going to get into more detail. I just want to cover the high level of the difference between this type and the other type of balancing valves. The one on the left is very similar. If you look inside, it has a similar kind of element. That's from a different manufacturer, and that one's been around for a while. It's not adjustable. You order it as a fixed temperature, and then the one on the right has an adjustment knob, so you can change the temperature in the riser circuit of the domestic recirc system. So is that it for me, Max? Oh, one more slide. Graphically, this is how the thermostatic balancing valve works. You can see on the x-axis there, when you have cooler water temperatures, the valve is open. And as those water temperatures increase, the valve will close down to a minimum flow rate. And then anything above that, the valve will stay at minimum. So that's how they work. In the recirc line, if a particular riser is too cool or cooler than it needs to be, that valve will be open to bring more of that recirc warm water into that circuit. And then as that riser gets satisfied, it will close down to minimum, which then pushes the water to the other secondary circuits in the system.
And so these valves never completely close. So there would be, minimum flow. So it's not going to deadhead a recirc pump or something like that, but it is going to be a very small opening at that point.
Exactly. They need to stay open so that that thermal element can respond to the water temperature. And this is a really nice picture here of a retrofit. These are great for retrofit, by the way. We see a lot of them installed in retrofit applications. This particular one, you'll notice, has a zone valve actuator. It's actually a thermal powered 24-volt on-off actuator, and that is a system that is using elevated temperature to do thermal disinfection of the recirc line. That little 24-volt actuator can be energized by a building automation system or anything really, just a 24-volt switch to pop open the balancing valve and allow increased flow through the circuit to do a good disinfection flush. And that is really only used if you're going to be employing or implementing that strategy of thermal disinfection to control Legionella.
Yep, so there are a few different variants of that valve, and then also you can see the nice temperature gauge there to verify that you've got the right temperature, just even without getting on the ladder or anything like that in a retrofit.
Right. This 116 series thermosetter has a dry well there, so that little temperature gauge is just stuck into a dry well. And if you're using a building automation system, you can put a little 1/4 inch, what we used to call a bullet sensor, in that dry well. It's a 1/4 inch. Just put some thermal conducting compound in there, insert the sensor and run that back to the BAS, and then you can monitor the temperature in all of your risers in the domestic recirc system, which is convenient. So, and that's a standard thing. It comes with the dry well, and the gauge is optional.
Great. Okay.
So then when you get a system balanced with the thermal balancing valve, this is what it would look like, for example. So in this picture, you could see that each of those risers would be controlled at the set point for that that 116 series, and that image happens to have the little 24-volt actuator on there too. So the little bypass cartridge is shown in this schematic. And these are really handy for saving energy. And how does that work? If you use a smart pump, you can see that circulator there. If that is a smart circulator, it will respond to the opening and closing modulation of those thermostatic balancing valves to save energy. So when all of the circuits are up to set point, like this diagram shows here, that pump can just coast and operate at very low wattage and conserve energy.
And we had some pre-submitted questions about pumps as well. So I think the easiest advice here would be to get with your pump manufacturer, whichever brand you use, and see what setting might be the right pick for this type of modulation. So if you know that you are going to be maintaining temperature in all the risers, you can kind of talk through that with your pump manufacturer and find the right program there, because like Kevin was saying, best case scenario is we've got consistent temperature to all these risers and we're not overdoing it. We're not over pumping. We're not storing the tank at 180 degrees if we don't need to. So just kind of the bare minimum to keep everybody happy. And these valves will really help smooth that out a lot. So.
Right. These are my favorite balancing valve for domestic recirc.
Yeah, I think it's a great fit. So why don't we switch over to sizing? I'm going to bring Cody in. Do you want to go over some sizing details for manual valves with us?
Perfect. Yeah, I can definitely do that. Thanks, Kevin, for going over the different types of balancing valves. Now we're going to talk about choosing the right size of balancing valves. And one of the biggest problems we run into with this type of application or balancing valves in general is that, or any type of valve for that matter, is people just want to size it based on pipe size. And that's not always the case. So when you're looking at your differential pressure type balancing valves, or as Kevin referred to them as your pressure dependent type balancing valves, you really have equal potential for trouble in either scenario if you are under or oversizing them. If undersized, the valve will have to be near closed in order to have any control over the circuit, and this typically leads to very unstable operation. It also makes for a much more difficult time when commissioning, as very small adjustments of the knob to the valve or changes in differential pressure from the circulator or in the system can have drastic impacts on your flow rate. Now, undersizing will give you more control over the circuit, but it also leads to more pressure drop, which is going to require a little more oomph from your circulator. So obviously you got to find that nice little balance in there. You can see the nice little graph there that goes over your basically what amounts to your valve's authority and how it's actually reacting and based on how you're adjusting the valve versus the actual flow requirement. And you'll notice that when you go from basically closed to 10% of the valve travel, the stem travel, you're actually going from 0 to 30% of its flow capabilities. Whereas if you're kind of in the middle of that line, very similar, it's kind of like a pump curve. You want to kind of try to be in the middle of that in a lot of cases. But if you're going from 30 to 40% stem travel, it's a lot smaller of a window. So again, as you're going from that near closed to slightly open, it's really difficult to get it just right because again, very little changes, whether it be you adjusting the knob or something happening throughout the system, can have really drastic examples there. So you want to make sure that you're sizing it correctly, so that way you're giving yourself an easier time with those pressure dependent type balancing valves. So you'll also, go ahead, Max.
I was going to say that's something that's probably across the catalog, that pipe size does not necessarily mean it's the right valve size if it's
Bingo. Yeah.
a mixing valve or a balancing valve or anything like that.
Yeah, I was going to say, if I had a nickel for every time I heard anybody say I need a 2-inch mixing valve, and you say, well, what is your flow rate requirement? And they're like, I have no idea. It's a 2-inch pipe. Give me a 2-inch mixing valve. So,
yeah.
But you'll notice there that with that curve that's on there for that pressure dependent balancing valve, you'll notice that some of them have different curves, and you'll notice how it notes in there about valve authority. And so as that curve kind of bends upwards to the upper left, you've got less valve authority in there and basically less control over the circuit. And as that that curve kind of bends down towards the bottom right, that's where you're going to have even more valve authority. And again, you're going to have more resolution and more definition in those turns and less drastic changes as you turn it, which is just going to make life a lot easier when again setting them up and making changes in the system. If you use something over here, it's not going to have as drastic of an impact over here. Now, when you look at your direct reading type balancing valves like our quick setter, these are really very simple. Okay, you're just going to want to make sure that your required flow rate for the circuit is covered in the flow meter. Pretty straightforward. Okay, now I would use good judgment, just noting my previous comments on oversizing, as many of the flow meters that we have, say 1/2 to 3/4 to 1 inch models, they might have a little bit of overlap in the flow meters. So just because you've got an 1.25 inch model and it has a flow meter between 5 and 19 gallons per minute, and it can read 5.5 gallons per minute on the flow meter, that doesn't necessarily mean it's your best choice. A 3/4 inch model with a flow meter capable of reading 2 to 7 gallons per minute will likely be better suited and have a little more control over the circuit. And the bonus there is that it's going to be a little bit cheaper than an 1.25 inch model as well. So, and it's also going to be a little bit more stable if, again, differential pressure changes in the system, if you're using like a standard single speed type circulator. So again, I know Dan will kind of note this, the difference between those pressure dependent type balancing valves versus the flow meter type balancing valves is it's all in the labor, and it's going to make your life a lot easier, and Dan will go over that later. So we'll move on to your pressure independent type balancing valves as well as your thermal balancing valves. Now, with the pressure independent balancing valves, again, it's not just a matter of knowing the right pipe size, but it does get a lot easier when we start talking about these ones. When you've got a valve like our 127 series FlowCal, it's literally just a matter of choosing the correct flow rate for the cartridge. After that, the only requirement is going to be making sure that your valve is operating within its control range, like Kevin had mentioned before. So all pressure independent balancing valves will have a control range. Sometimes it's 2 to 14, 2 to 32, 2 to 64, whatever the case may be. But what you're going to want here is just to make sure that you have at least the minimum of 2 psi pressure drop across that valve, again, to make sure it's within that control range. So this means you're going to be adding roughly 5 feet of head to your circulator requirements when sizing your circulator to again, make sure that you are in that control range for that pressure independent balancing valves. Now, as for thermal balancing valves, and very specifically for domestic hot water recirc application, sizing is also pretty simple. You're still going to go about the same business as an engineer or designer of figuring out the flow rate requirements based on your heat loss of the system and the desired temperature you'd like to maintain at that last fixture and everything. But now you've got a valve that's going to modulate. So how on earth do you size your circulator based on your head requirements of that loop and everything else when you've got a valve that's moving up and down and doing its thing? But what you'll notice is that in our sizing charts there, we've got multiple different lines. We've got a minimum, we've got a maximum, we've got a thermal disinfection mode, and we've also got a design line there, which is a 0.52 CV for this particular model. I believe it's 0.52. It's hard for me to read there. But what you're going to do is you're going to figure out what your flow rate requirement is. You're going to use that design CV line and figuring out what your pressure drop is using that design CV line. So again, you'll just add that to your circulator requirements when sizing, and your life is going to be pretty easy. Now, again, it's not going to make your jobs that much easier on the design side. You still got to figure out the head loss of the circuit. You still got to figure out, the right sizing and everything of your circulator. But where it's really going to shine, just like the pressure independent balancing valve, is that it's going to take a lot of the work out of it in the field. And again, Dan will talk about that later as well. So again, the different types of valves, not just sizing, you want to make sure you're doing it correctly. And I think we're going to pass things back on to Dan. Is that right, Max?
Yeah, so Dan, do you want to go over how we set up these different valves? And you can start with the manual style here.
Yeah. Thanks everybody. Thanks, Cody. So you've listened to Kevin. You've picked the right valve for your project. You've taken Cody's advice and you've sized it right. So now you have it installed, and how are you going to set that thing up? How are you going to make it work properly in your system? So when you look at the manual, the pressure dependent valve, this is probably going to be possibly the most challenging to set up. I mean, it's going to require you to have a flow or pressure drop chart for each specific valve, or hydraulic characteristic sheet for each valve, keeping in mind that, you know, the different model valves and the different size valves require a different chart. So, you know, as you're going through your project and you might have a 1/2-inch model and a 3/4 inch model and maybe up to a 2-inch model installed, as you're setting them up, you're going to make sure you have the correct flow characteristic chart for the proper valve that you're working on. From there, you're going to need a manometer, you know, pressure differential meter to measure the pressure differential across the valve. You know, and that pressure differential is going to give you your pressure drop through the valve. So once you've calculated that, that's where you're going to refer back to your chart to match the pressure differential to the flow rate that you're getting through that valve. That's what's going to, you know, correspond. How much flow you're getting through that valve is based on that pressure drop, and then you'll make your adjustments to get the correct flow rate you need based on the pressure drop that you're seeing on your manometer. So that's going to probably take the most time to set up. Again, moving from valve to connecting your tools, referring to your chart, that's gonna probably take the most time and effort. And then once you get, you know, the system balanced, you may need to go back through and check the ones you've previously set up, just to make sure that as the pressure in the system has changed, that the valve settings hasn't changed, or there's no additional adjustments that need to be done. Also, it may require, you know, some jurisdictions require a third-party balancing contractor to be brought in. In fact, I think, you know, we were talking about it, and there's certain areas that won't even allow the installing contractor to be the balancing contractor, or even allow them on site when the balancing contractor is there. So, you know, from a timing and cost standpoint, bringing in another contractor and scheduling another contractor on a project may add additional time. So this
like
one,
an audit or something, that you've got a different team coming through. And I guess if, you know, it depends on who is required for the scope, that if you're the mechanical contractor and you're also balancing, this may be less expensive material potentially, but you're adding a lot of labor. So if you're not doing the balancing and your scope is to put balancing valves in, sometimes people will go with this. And then if you're in charge of doing all of it from the contractor standpoint, then the other options may be better. But yeah, sorry, did you have anything else that you wanted to cover?
Right. No, well, you're right. You talk about scheduling too. You know, projects have deadlines, and now you're relying on a balancing contractor to come in a timely manner and get that project balanced. That just adds to the project.
We were actually on the next slide here, we were talking about a job site a couple days ago where they had a big complex, and it was 1,400 of these valves. And if you can imagine taking a manometer to all of the manual valves and then back through or adjusting something and having to start over, I mean, that's a huge amount of work versus just pulling in here. So
yeah, making sure you have the right flow chart for the valve that you're working on, it just adds time and effort. So then when we look at our direct reading balancing valve, it gets quite a bit easier to balance. It's only going to require a small wrench, can be installed in any configuration, so very easy to get to read the pressure gauge. You're just simply going to pull the pin, hold the pin, you'll register what your current flow rate is going through that valve, and then with the small wrench you'll make the adjustment until that ball drops to your desired flow rate. Once that's set, you'll set your memory pointer so that at any given point, if somebody comes in and makes a change or wants to check the pressure, you know, they'll see what it was originally set up for, and then release the pin, and the valve is in service and balanced. At any given point, you can come back through the system, simply pull the pin, read the registered flow rate through the valve, or anybody can do that. I mean, you could have a maintenance contractor or anybody coming through there, pulling the pin and verifying what the flow rate is set up to through that balancing valve.
Yeah, if an engineer wants to commission or whatever.
Sorry, Max, that temperature gauge is also in a dry well, like I mentioned earlier, so you can just slide that temperature gauge out too. It's a dry well.
Yep.
And like Dan mentioned, this is upside down, and the ball is on that magnet inside the fluid stream. So it's not like that ball falls to the bottom because of gravity. So you can install it upside down and it works the same because it's following the magnet, not gravity based.
Yeah, this can be installed in any configuration. So very easy to install it so that you can access it, adjust it, or check it at any time.
Great. Okay,
So then,
what about these?
yeah, so then the thermostatic balancing valves, again, one of the easier ones to set. What's nice about these is you're setting it based on the temperature you want coming back through that return loop. So it's easy to even pre-adjust prior to installation. You can set it, you can lock it, and then install it. You don't have to have it in place to install. At any given point, you could come back and make an adjustment if you need to. And very simple. I mean, it does have, we do offer it with a temperature gauge on the outlet so that you can verify what the temperature is going through that valve.
And if you are worried that someone's going to adjust it, so this locking cap, you take that off and then you just kind of straddle that piece right there. Do you want to explain how that works so it doesn't move?
Yeah, you simply, again, loosen the screw, and that's all it really takes to set it is a screwdriver, because you can loosen the screw, back the cap off. There's a little notch that you can lock that cap onto and then put the screw back in place, and it will prevent that from being tampered or adjusted in the field.
So it still has the ability to adjust, but if you are supposed to be doing that,
right,
not just someone who's going to come turn all the knobs.
Kind of prevents anybody from coming through and making an adjustment on that.
Yeah.
Well, I was going to say too, Max and Dan, this is another great tool here. This could be preset before it even got out to the job and locked in place. So, I mean, if you really wanted to make life easier on the install guys, if you know they're all going to be set to 110, set them all to 110 and lock them. And then all they got to do is put them in the pipe, which is going to make life even easier.
Right. Yep. Send them right out to the job preset.
Perfect. Okay, let's take a look here.
So then future adjustments, let's say something in the system changes, or there's, an addition to your recirc line and you need to add another circuit or balance. With the direct reading balancing valve, it's very easy to add an additional valve. One thing you're going to want to make sure is that your pump and piping is sized to be able to handle whatever you're adding to the system. But once that's done, a direct reading valve is very easy to add. Simply pull that pin, set the proper flow rate. You can go back through the system and check any of the ones before that just to make sure that they're all reading where and balanced where they need to be. The thermal balancing valve, again, very easy. Simply, set your temperature and install it. You can pre-adjust it and set it before it's even installed. So as long as your piping system and pump is sized to be able to handle the additional circuit or addition, you won't have any issues there. When you get to the manual balancing valve, this is where it's going to be a little bit more challenging. You're going to, again, need your manometer back on site. You may need to bring that balancing contractor back out, set up the new valve, but then you may have to go back through your system and check the valves that were installed before that, just to make sure that, maybe changing your pump size or some piping sizing to add a circuit didn't change how the valves before that were balanced. So it's going to take the most time and effort.
Yeah, and I would say that if you were doing any sort of retrofit, adding a manual balancing valve is going to be potentially the trickiest, where we've had a couple projects that were never really balanced to start with, and to go back with a thermal or a direct reading is much easier if you don't 100% know where everything's going. And you can just say, okay, this riser needs 120 degrees, period, and we don't have to go back through everything. So that's definitely retrofit friendly.
Yeah, absolutely.
Okay, so Cody, why don't I have you kind of go through this example, and then we've got a job site next that we'll talk about as well.
For sure. So obviously, balancing valves is something that everybody uses on a lot of hydronic and domestic hot water recirc applications. But what happens when you don't balance properly? Obviously, if you are putting in a circulator into a closed loop system, and for the sake of argument, we'll talk about a domestic hot water recirc as a closed loop, because I mean, really that's what it is. It's just going around in a circle. But you look at a hydronic application or a recirc application, and you got that closed loop type system. And the water's lazy. It wants to take the path of least resistance. It wants to make its way back to the suction side of that circulator as fast as possible. And when you've got some of these big sprawling buildings and things like that, it's going to want to take that closest circuit and come right back again, versus going out further and further and further to the, the outermost extremities of a building. And, what happens with this in a lot of cases is, say you've got that first riser there that Max has got his mouse right on there. You've got the flow that you need, that 1 gallon per minute, probably even more flow than what you need. That second riser, you've got a 0.5 gallon per minute. And then, that last one, again, it's where there's the most resistance, and you're going to get the least amount of flow through that guy. And balancing can help basically even that all out. And this is the same idea with hydronics as well. I mean, if you don't have balancing, you're going to get too much flow in this fan coil here and no flow in this fan coil here, which is going to lead to a lot of uncomfortable people. Now with domestic hot water recirc, you're going to just lead to really impatient and grumpy people, because they're going to be waiting for their hot water at their taps and everything like that. But it also leads to other problems, because the general consensus here is that if I don't have enough flow out to my last fixture or my furthest riser or anything like that, people don't really think like, hey, I should probably balance this a little bit better. No, they think, man, I need a bigger circulator, because that's the end all be all discussion here. Just, more cowbell, throw it right at that system, but really in all reality, it's just a balancing issue. And circulators, by adding to those circulators, you're just making the problem even worse. And you're going to lead to even more problems with velocity noise and potential for erosion corrosion with copper piping and things like that. And even if you look at certain piping materials like PEX, for example, if you were putting PEX into a dedicated recirc line, there are a lot of the manufacturers out there that are limiting dedicated recirc lines for domestic hot water to 2 feet per second velocities, okay, which is going to be a lot lower than most of your hydronic applications for flow rates, just because you've got that hot, high temperature chlorinated water and everything like that. But we had a really cool example here. If you can go to the next slide there, Max. We had a cool example here that was actually a job that was out in Denver. It was a multi-family building, really interesting job here. And I actually visited this job, and I was with a great industry colleague, Mark Etherton, and he is an incredibly smart man. And he was brought into this job because this job, I think this building is probably about 40 years old, and it has been through several remodels, several building maintenance guys, several, oh gosh, just if those walls could talk, I mean, they would tell you a terrible, terrible story. And they were in this exact same predicament. They were dealing with, unequal flow rates through their risers. The tenants were not getting the domestic hot water that they needed, and they were just kind of band-aiding it all over and over and over again. Now, this particular building is what's referred to, the piping schematic there that you can see in the lower right is kind of a pyramidic return. So you've already got kind of a really messy one right there to begin with, because every single riser has a very different head requirement to get through there with the same flow rate, versus maybe say like a reverse return. Now, reverse return may not necessarily solve all your problems. It could make things a little bit better, but the idea that every single riser on a reverse return system in a building of this size is going to have the exact same head loss it's ridiculous. The idea that you can only add 1 elbow to every riser or 2 elbows to every riser, they all have to be the same length and everything else. It's just not feasible. So in this case, they had a pyramidic return, and they actually had 28 recirc branches coming off of this system, coming back to a common return, going right back down to their water heater. Okay. Now, in this particular case, all they had in that system was ball valves on every single one of those recirc branches, and every single one of them was wide open. Okay. And all of them were wide open, and it was just an ugly, ugly mess, because again, they couldn't get the right flow rates. Now, this problem was made even worse by the fact that they had a lot of cross connections in this older system. They had a lot of single handle faucet cartridges that were crossing over from hot to cold. And so there were points on some of these risers where they had a bad enough cross connection to where everybody else on the rest of that riser could not get hot water, period. And what's really interesting about this job, and if you want to really light a fire under somebody's rear end, is they were having this problem for years, absolutely years. And what ended up happening was one of the tenants actually ended up calling the Denver Health Department, and the Denver Health Department came in and said, look, if you cannot provide the proper temperature domestic hot water, you're going to have to take all these tenants and put them up in hotels. And ooh, man, I've never seen anybody move so fast. I mean, they don't want to pay for the hotels for all those people. And that's a big building, and it was full. It was full. So they really moved into action in that particular job. They ended up finding all those cross connections, and they fixed all those. And then from there, they actually put in 28 of our thermostatic balancing valves. And this was a great valve for this application because this building had been reworked and scabbed over many, many, many times. You talk about oversizing the circulator. Again, before the balancing valves got put in, they thought to themselves, well, this is a great idea. We can put in a bigger circulator. Well, then they just created another full-time job for the maintenance guys because they were out there replacing copper piping that was, pinholing and all that other fun stuff. It was a huge, huge mess. So in the end, they ended up fixing all those cross connections. They put in balancing valves. And I think one of the most interesting points to this entire case study type, and to backtrack, we actually did a webinar on this. It was kind of a case study webinar with Mark. So if you look through our archives on YouTube, you'll find Mark Etherton on there. Very, very smart man, and he's a great listen. So definitely check that out. But what I thought was the most interesting comment about this whole thing is that from 1 month to the next, they actually saved, I believe it was like 20 or 30% on their water bill for this building. It was astronomical. And you think how much, if they would have done that sooner, how much the repairs could have already paid for themselves. But what's interesting about that is that every tenant, you talk to them about it in the building, and they would literally turn on their bath faucet, and they would go away and make their breakfast, eat their breakfast, put the dishes in the dishwasher, and come back. They still wouldn't have hot water. And you think about all the water that's being wasted there. It was just absolutely crazy. And so, great case study with this guy. Again, going from ball valves being wide open to balancing valves to fixing the cross connections and really doing this system justice. And now the tenants have something else hopefully to complain about in the buildings, and not the hot water anymore, which is fantastic. So,
and you had mentioned a couple things. I'll go back to this picture. So the pinholes, if you just triple the size of that pump, you're not solving any of those issues that Cody mentioned, except you're now creating these new pinholes behind sheetrock or whatever. And it's not even a specific material problem as much as it's just a plumbing pipe problem. It could be copper, it could be PEX, it could be CPVC. Just increasing the velocity through the roof doesn't solve anything, and it actually creates more problems. And then the other thing that we've heard before too is that, well, if this is properly balanced, you don't need any sort of thermal balancing valve or anything like that. If it's balanced per the engineering recommendations, it's going to be fine. I think that works on paper, and it may work in reality, but this riser may have one tenant, and this riser may have a full house on. It's completely dynamic. So these the thermostator was a great pick for this because it's dynamically adjusting to the dynamic tenants in a really complicated, really confusing building that was not designed properly, in that all of the returns aren't, it's not a reverse return, it's not the same length, it's not the same number of fixtures, but they're just on and off at different times too. So if you put the thermostators in and say we want this specific temperature on each riser, they may be open all the time, or they may be way down in their range closed all the time, depending on the tenants, but at least you're not over pumping it, and you're getting the right temperature to all those weird places. So definitely the right pick for this application. One of the things that we've talked about too before is throttling, balancing with a ball valve. So a ball valve is going to have a smaller adjustment range. Something like our thermostator has a ball to do the adjustment, but it also has that additional window to see what the range is. It has the venturi. It's kind of built to be more than a ball valve. If you're trying to balance this type of system with just a ball valve and you have it choked way down, it may erode past the edge of that ball valve and then not even work to shut off the flow. And it has a really small adjustment range because it's just not really what it was meant to do in some sense. So these other options are better, and even just the ball valve of the quick setter is really meant to be a balancing valve, where a ball valve by itself isn't, I guess. So those are a couple things to add there.
I think a great way to, you talk about balancing valves and ball valves and stuff like that. Ball valves have what is referred to as typically a quick opening characteristic. And I talked about that before with that curve that was on that sizing or that chart for the pressure dependent type balancing valves, is that when you go from 0% open to 10% open, that's 30% of the flow or 40% of the flow, and trying to do that with a ball valve, you know, it's kind of like when I was doing refrigeration, you'd feel the suction line and be like, oh, that's beer can cold,
Beer can
that's
cold,
perfect,
yeah,
you know.
you're good there.
And that's no way to do it, you know. And not only that, you look at a ball valve like that, and you see any maintenance guy with, you know, with a couple of brain cells between his ears is going to look at that ball valve that's about 7/8 closed and go, that ain't right. And he's either going to completely close it or he's going to completely open it.
Yeah.
And it's, you know, there's no way you're going to be able to save that one. You know, so I mean, there's a lot of different things in here that, you know, could come into effect. But yeah, this was a great application, and I thought it was a really cool one, and I was really happy to be part of it because it was just interesting to see the outcome with that one, and how much that could really save, you know,
Yeah, so
time
no
and money and everything else.
no complaints from the tenants because they've got hot water. And then, you know, imagine what I think in Etherton's webinar, he says what the dollar amount was for the money that they were
Yeah, I
saving on
can't
the
remember
water
what it
bill.
was though, but
It was substantial. I mean, it
was a
probably
lot.
going to be a quick payback for, you know, installing those valves and not
Yep.
having all the leaks from the pinholes and things like that. So yeah, really cool case study, really good problem solving on behalf of the contractors there. And yeah, so that was a great fit. So I think that takes us to the end of the presentation. Do you guys want to add anything else before I go to kind of the wrap up slides?
No, I think we had a lot of great questions in this webinar, Max. I was kind of keeping an eye on them in the background. A lot of it was about, you know, pump applications and settings on your circulators and things like that, which I think, again, going back to your pump rep or your pump manufacturer, I think would be a great idea, you know, as far as whether you're doing constant differential or any type of an auto type mode or anything like that, you know, and even, you know, some of your delta T modes, because I mean, you look at like a pressure dependent type balancing valve and you put that in conjunction with a delta T mode on a circulator, you've got a circulator that's varying all over the place, and now all of a sudden you got a fixed orifice balancing valve that's not moving, and so you know, you took all that time to balance it when in all reality the circulator's doing whatever it wants. And I mean, I definitely talk to your pump reps and your pump manufacturers about that. They're obviously going to be the experts on their controls, but I think, you know, in a lot of cases your pressure controlling type modes and constant pressure type modes are going to be where it's at.
And then if you've got questions about, you know, I mean, about the system in general, but about selecting or sizing a balancing valve for your application, here are some of the faces of the people on the phone that you'll call when you call tech support. If you say, hey, I've got a hotel building that's 20 years old and it's really struggling with XYZ, here's what they've done. We're going to be able to help you figure out what the right valve is. And then also, hey, you need to go from 1 inch to 3/4 for the flow rates that you're talking about or something like that. So we can walk you through that because it is complicated. And the reason we have a couple different balancing valves in the catalog is there's not a one size fits all, and it depends on the application, and we can help walk you through that kind of case specific with the techsupport.us@caleffi.com, or give us a call. So yeah, let us know if you need anything with that. And then I will wrap up here. Just another mention that the air-to-water heat pump system, Hydronic, is live in this digital format as well as it is shipping. And then stay in touch with us on social media. We love to see your job site photos specifically. If you post something cool, I'll probably be reaching out to you to see if we can get some more pictures or write up a case study about it, because that's what we love to hear is, you know, the success stories from the field. We can talk about the charts and graphs, but really seeing that somebody can make a difference in a, you know, hotel or something that had struggled is a big win for us. So here are different handles for social media. And that takes us to the end of the presentation. So thank you for joining us today, and we'll see you next month.
Thanks, guys.
Thanks,
Thank you.
Max. Bye, everybody.